Now if this is no, there is no, let me remove this thing so that it is quite clear. So now I have chosen a somewhere there. It is up to us because we have to bracket the root. We have to say, okay, there exists a root in this interval, but we don't know where it is lying. So if I check this condition, I can still say both are above the x-axis. So they will be a positive. It will be a positive, and we multiply. I will get the answer greater than 0. So according to our conclusion, I said may or may not. In the last case, when I plot the A here, I showed that it does not contain any root. Root means the point where the graph is cutting the x-axis, and it was not cutting the x-axis at that time. But now, if I selected this A and A, so I will get still a positive answer. But I don't know whether the root exists or not, because it, and but from the picture it is quite clear root exists at least at 2 points there and there within this interval A to B. But so how do we distinguish whether really a root exists or not? Because we will get the final answer f of a into f of b, but we cannot distinguish which case is happening, whether it is a root or it is not a root. So this condition is confusing. This condition equal to 0 is very easy. You have find the root. There is no need of bracketing. This condition is confusing. You may have, you may not have. So we need certain condition that can tell us exactly that, okay, between a and b, including a and b, there exists a root. That's what we call a bracket. We have bracket the root. Okay, so bracket means we have covered the root. So how do we do that? So in the third case, if we have this third case, I will remove that part in the later slide, or maybe I will redraw this diagram on the next slide. Let's see. But this concept is very important called bracketing. It will be used in the other methods as well. It is, I'm explaining is with reference to the bisection method, but it is a general concept. Okay, because we are just bracketing at the moment. We are saying, okay, this is A, this is B, one root or many root exists between them. We don't know uh, how to find that root at the moment and where it is exactly locating. Because if I say that A is this, B and this, and these are the points, there exist billions of trillions of, and you can continue counting bill points. I don't know where are these 2 points exist, which are the roots, but we have bracketed to certain extent. We need some logic that can confidently let us know where the root exists or not exist in the case. So in this case, there is a third possibility left, and that is related to a less than 0 case. So if f of a, f of b is less than 0, for example, so what will happen? In this first case, we have a root. In this case, we may not. It is confusing. Let's understand this thing. But first, we have to understand if I multiply the value of the function at 2 points A and B, and the answer is less than 0, when will it happen? It will only happen then if it is negative. Whatever be the answer is negative, let's say minus 20, minus 30, and it is positive, then we will get less than 0 because plus minus multiply negative. Similarly, if it is positive, then this must be negative. In other words, they have to have a different signs. Okay, so if this situation arises, let's say, let's understand first when will this situation happen. For example, this is the graph of a certain function. So I selected a point here by mistake or by any reason, and b point here. So now what will happen? We know that this is positive y-axis and this is negative y-axis. So all the values which are above is positive and all the values which are negative. So if I computed this quantity, I will get f of a. And if I compute that quantity, I will get f of b. But I know that this f of b is negative because it's a less than, it may be a minus 10 or minus 20 or something. So in that case, if I compute f of a into f of b, I will get an answer which is less than 0. F of a, f of b must be a less than 0 in this case. So this means that if I have a which is one is positive and other is negative, or other way around, if the graph is something like that, you have a different conclusion. So it does not matter whether which is positive, which is negative. One has to positive, other has to negative. So uh, so this is less than 0. But what is happening now? We can clearly see if this condition holds, then we have a one conclusion, which is very helpful for us. We can say that if this has happened, then there exists at least, if this important word is at least, there exists at least one root. There exists at least one root uh, between A and B. So what we have done, we have bracketed the root. We don't know still the location where it exists, but we know that there exists some root between A and B. Maybe it is lying here, 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 anywhere, but there exists. Why? Because the function has changed its sign. It's become negative. It become negative from positive. As we move in x direction from A to B, we can see that the y values are decreasing, but positive, positive, and suddenly it becomes zero, and then it starts to increasing again but in a negative sign. This means that whenever we have this condition, this means that in between A and B there exists at least one root. कम से कम एक root लाजमी होगा. Okay, that's what we want to say. It there exists maybe a three roots, there exists a maybe a five roots or 20 roots. It may exist many more roots, but that is for sure. If f of a into f of b is less than 0, there exists at least one root. That is for sure. And to use this method and other method, we have to make sure that there exists at least one root for this function. So that's process is called bracketing. Now the question is from where we will get a and b. No, it is a random process. You have to put the points in a and b, and you have to notice the sign. As soon as the sign has been changed, you can say that okay, from A to from B there exists one root. Okay, so in this graph A is positive and B is negative, but graph could be other way around as well. For example, like that. So A is negative, B is positive, both are okay. Okay, so I think it's better I will redraw the diagram for bisection method on the next slide, but concept is most important. So these all are linked together in the latter stage. So we are basically discussing bisection, but this bracketing concept is general concept and that could be used for other methods as well. So I have introduced this concept to you. Now, by how the bisection method works, basically bisection and all other methods that will be learned in the later stage basically try to find the approximate location of this root. If this is the root, so you can clearly see why I have drawn this diagram like that, because in that case I can say if I selected A here and B here, so A and B has at least one root because it's lying there. That's why I usually draw the graph like that whenever I want to explain the method. So this is called bracketing the root. Okay, this is one of the integral part of the finding the roots, but we don't know the location. Okay, it is something like if I say okay, from 0 to 1 there is one root, then your question is, sir, okay, 0 to 1 there exist billions of points, which one is exactly a root? That is, if I put that value in a function I will get exactly the answer equal to 0. We don't know it. But bracketing can help us that from the entire domain we do not need to have information about the entire domain to find the root. We just need that bracketing information. All the values which are greater than a and less than b must contain a root, but we have to find out where it has. Okay, so to find that root we have these methods. Okay, and how they work you will learn it now. So I'm going to redraw this diagram again. I can explain here as well. Okay, let's try this because it's not that difficult method. There is no derivation, I already told you. Okay, so if we do not have enough understanding, then we will do somewhere. So what I'm going to do now to explain you the bisection method. uh, so what we have in our case is that for example I selected A here. Okay, so do not ask me from where you got the A, and let's say I selected B somewhere there. It is a random choice. Okay, initially. So A and B. So one can clearly see, but I need to define those A and B. So what I'm saying A also belongs to the domain and B also belongs to the domain of the function. Okay, I think I should remove that part as well. It is no need for us. It is just for the your idea. Removing using a duster is much easier than this one. Okay, so Okay. Okay. So this one. So let's draw the line here. This is different. So now we have to understand the bisection method. So what I did, let's say I have a graph. I am explaining the concept of bisection method graphically, but we do not find the root graphically. We just have to do the calculation in the later stage. But let's understand the conceptual working of the bisection. So this is the point A and this is the point B. So one can clearly see from the graph that this property hold f of A, f of B is less than 0, which means that at least one root exists. Why? Because if I have a there and if I put there, so I will get f of a, which is negative in this case. It will be somewhere down. And similarly, if I put b in the equation, I will get f of b, which is above. Okay, so somewhere there it is negative and this is positive in this particular case. It could be other way around. For example, the graph is like that, the root is same, but then it is positive and it will be negative. So do not memorize it. It could be any possibility, but you have to make sure this condition. In this particular case, we can say this is negative and this is positive, whatever be the answer of this two one. So this we have this represent. Now how the bisection works, and you can understand from its name as well. So there is an interval from A to B. Okay, so interval we have is from A to B. What we do, we break this interval into two halves. Okay, that's why it's called interval halving. I have to bisect that interval. So this is A and this is B. So if I want to find the midpoint of the interval, which is obviously lying between A and B, you have learned in the statics as well. If you compute the mean of two numbers, it will lying between the two numbers. So so if I compute the mean of these two quantities A and B, so I will get something which is in the middle of these two numbers. That's called bisection, bisect. Or in case of interval, what I am doing now, I have half the interval. So interval starts from there and ends here. So I want to half that interval. So how do I do that? Very simple. Let's say the point which is lying in the roughly in the middle of this interval is C. The point is C. How do I compute that point? Very simple. C equal to, I have to add A plus B and have to divide by 2. Simple, very simple logic. So C is a point who has a numerical value equal to what? A plus B upon 2. So it is very simple, sir. You selected 2 points. One is negative on an answer, is other has a positive answer. Then you want to do, you have to compute it another point C by taking the midpoint of these two values. That's what you have done. Okay. Now, student, from there the logic starts. What do you think from this diagram? Although this is a dummy diagram, rough diagram, but what do you think? This C could be a root or not? Think about it. I'm not saying this is a root, but I'm saying based on this logic that you have to half the interval. So my question is, this could be a root or not? We know that exact root is XR. And if I know the XR, if I put them XR in a function, I will get equal to 0. But I don't know whether where it is situated. I know that it is situated between A and B. So I am trying to approximate that XR. I want to search for it. So what I am doing now, I said, okay, I find the midpoint of the interval which has bracket the root. And then what I'm doing, I'm saying maybe the C is a root. So your answer is yes, sir, it could be possible, but in this case it's not true. But yes, it is possible. Why? Because if I have selected A and B such that if I compute the midpoint, it will exactly lying on at the XR. Although it is very luckily, then it is not usually happen, but logic says yes, it is possible that you will get the exact answer. Because if I select A somewhere there, for example, then maybe the midpoint of A and B is exactly the XR, but we don't know the XR. Okay, so that's what we are working on it. So, but here in this particular case, I have not computed the reading. So now here we have to introduce our concept of error. So this is the exact value and this is the approximate value. Let's in bisection we claim that value C as a root. Although we can say this is not true, there exists a difference between the exact and the approximate. So this is basically the quantity is error at the first interval, because we have just performed this calculation one time. And obviously in a class of your class, if everyone is performing this task, then each of you can have a different C, because it depends on A and B. So everyone can bracket the root at differently. So that's why C could be a different. But point is, based on this logic, we may say that yes, we can have a root, but it's not a root, that is for sure. Okay, so question is how we can minimize, and we know that this gap is the error, basically the exact root and approximate root. Question is how we can minimize this error, which is only possible when by a certain logic we manage to move this point C very close to that value. If it is exactly coincided, it's a luckily it's a good thing, but not, then we have to move as much as close to this value. This is our task, and this is how the bisection works. Although bisection is already explained to you that we have half the intervals, but this is not the case. Can we make it much better? So from there we have a new concept, and the concept is called iteration. And iteration lies on a simple concept, and it is a question to ourselves that if we repeat the same process again, do we get closer to the root or not? Your answer is, what do you mean by again? So answer, we, for example, I have selected initially A and B, and I have found the point C. Now I have a two intervals, that's why it's called halving. I have half the interval. I have one interval there, A to C, and the other interval is C to B. You can clearly see from the diagram the root lies between A and C, in between A and C. Where I don't know, but it is somewhere in between A and C. So if I repeat this process again, that is compute the midpoint of A and C, it will be somewhere there. Okay. So what do you think? I am still repeating the bisection, but in a systematic way. So what will happen? This point, for example, this point, if I find the midpoint of A and C again, I will get this point, and I can clearly see this point is much closer to the root as compared to this point. And similarly, if I continue this process again and again, that is iteration, refining the same process again and again, such that you will get a certain better approximation or the desired approximation. So we can know that this bracketing technique always guarantee that root lies in it, and we are going to halve the interval. So whenever we halve the interval, we will getting closer to the root if we incorporate this condition every time. So what we'll do in the next iteration, I have this interval, I got the two intervals. A root may lie between A and C, or a root may lie between C and B. So I will apply this process on both intervals. So I can say f of A, f of C into, and similarly I will compute f of C into f of B. So I can clearly see if I compute f of C into f of B, both are positive. So this will be a greater than 0. So this is not the condition of our choice. Let's check this one, f of A into f of C. So f of A is positive, sorry, negative, and f of C would be positive because it is lying the other side of the root. So this would be positive. So if I multiply them, I will get the answer less than 0 because it is negative and this is positive. So in this case, what we have, we can say that, okay, so we are having a situation there, f of A. So this means that the root lies between A and C. So if I compute the midpoint of A and C again, for example, I will get a point D. So point D is somewhere there. Okay, then I have to repeat the process again because every interval will be divided into two intervals. Then for each interval, I have to check this thing and I will minimizing my error. What is happening now? For example, student, in the initial, I have 100 points. So when I halve the interval, I remove 50 points from it. Now I have to search the root between the 50 points, and then I halve it further. So I got only 25 points. Now I have to search for those between these 25 points. So I will get 12.5 points. So what is happening in every iteration, when I'm repeating the same process again and again, I am getting a better approximation, but I am reducing the interval to half. Okay. So what you can do, you can think about like, if you have to search something in a 1 kilometer, you are searching someone for a 1 kilometer, what you can do, you can divide into two portions. Okay. So if you do not find something in a one portion, then it is quite sure it will be in the other portion. So once you reach to the other portion, you divide that portion into a further half and you search it, and you found that okay, in the one portion you didn't find anything, then it will be in the other portion. So if you continue like that, you will reach to the root ultimately. And this is whole the concept of the bisection method. It is not a one time method. It will give you approximate answer, but by the process called iteration. That is, it is repeating one step again and again, again and again, so that you can get the better approximation. In each iteration, I am doing the same calculation. I am taking the midpoint of the interval by comparing this thing. I'm not doing anything new. So that's why it is an iterative scheme. You are doing the same calculation with the same logic, with the same intention that you will get the best answer. So this is the whole process of the bisection method. So what you do, you compute A, B, you find midpoint, then midpoint gives you the two intervals. You have to look for the possible root in the interval. Then you have to further divide into two. Then you have to look for further divide, and you will continue unless until you will reach very close to the XR. Okay, so as soon as you reach to the very close to the XR, in that case you can say that okay, we have managed to find the root. Okay, we have managed to find a root of the equation. Okay, but this could gives you the exact answer, but it's not necessary. So what you need, we need some stopping criteria. Stopping criteria is this, where we have to stop, because in case of iteration you are doing something like that. You have A, B, you compute it C by using the following condition. This gives you two intervals, A, C, C, B, for example, and then you check, you found that there is no root there, root is there, then you have to find another midpoint. Okay, let's call it D. Then you will get two sub intervals from there. So you get A to D and D to C. Then you, let's say you find the root that there is no root in this interval. So there is an interval. Now you have to divide that interval further into two. Okay, and let's say you got E. So now you have a two sub intervals, D to E, E to D to E, and E to C. Now you find that there is no root in this side. So then you have to do the same process. D plus B by 2, you get F. And then, so what are you doing? You are doing the same thing. You are dividing the interval again and again, equal parts, and you are trying to find the, this is also called linear search as well. But you are doing the binary search, sorry. So you are doing the binary search here. But this is also going to give you the root ultimately. But question is where to stop, because this process may continue. You have to bisect the interval every time. You can do it infinite many times. So there must be a stopping criteria. Okay, so that is where to stop. Which answer we can say, okay, this is much better. So in our book, you can find a different criteria, criterion that you can use. Okay, criteria is just a definition that you say, okay, if because it is very difficult to find the exact root, but if the root has the following characteristic, we can say that okay, this is okay for our calculation. This is something that we have to define. So stopping criteria, what is stopping criteria in this case? So stopping criteria, you can define it different way. You can read the book. What I am using in this case is based on the definition of the roots root definition. You remember the definition of the root? I said if you claim any value as a root of the equation, then if you put that value in the function, you must get answer equal to 0. This is the definition of the root. So what I want to do here, I said if you want to claim that okay, C is the root, for example, after you want to say let C is a root after n iterations. Okay, let's say you want to say, okay, after performing 5 iterations you want to claim that, okay, this is a desirable root, so there must be a definition. So I am defining my definition based on the root of the function. What is this root says? It says if this is the root you want to claim of the function y equal to f of x, this is the function nonlinear. You try to find the root by using bisection method, and you know that you have to perform iterations, but you have to stop somewhere. So you are defining a criteria based on the definition of the root. So I have defined like that. If I said if f of c is computed, then if it is exactly a root, so we all know this answer must be equal to 0. This is the ideal situation, but this is not going to happen because we may have exact root, but usually do not have. We have a approximate answer. So this is not going to be equal to 0 in this case. Or if it is equal to 0, you are lucky that you have got the exact answer. But method guaranteed that it can reach to the exact answer as well, but you need many iterations. So how we can say that, okay, which one is the definition? So I am defining the definition stopping criteria based on the definition like that. So I'm saying after performing n iterations, if I said that, okay, this is the root, then the absolute value of this quantity must be less than or equal to certain tolerance amount given to us. uh, Now you may are confused, sir, what is tolerance suddenly? For example, I said that I will consider solve or try to find the root of this equation, and but you have to stop at a certain level when you have the following accuracy. I said that, for example, I said if f of c is any value that you want to claim as a root or you want to use as a root. So before stopping, you have to check it. So you are checking. You said, okay, if I have a c, I put it in a function of a nonlinear equation, I will get certain answer. So you may get a positive answer or a negative answer. We are not interested in a sign, so I'm taking the absolute. I'm only interested in a magnitude. Already discussed in the case of errors. It is not error, but I have discussed the positive. So I will get a magnitude only. I'm not. What does means here, by the way? If I'm here d, so I will get a negative answer. If I here, I will get the positive answer. So if I'm claiming a certain value as a root, so I'm not interested whether that root is the right hand side of the exact value or the left hand side. I am only interested to know how far it is from the how far it is. So what is I'm defining the value of that function. So I'm saying f of c modulus. Okay, this is modulus, that is for only positive value is less than, for example, I said how we do it is up to us. We select this quantity. We have to define, we select this quantity. So we said, okay, 10 to the power minus 2. So we will claim any value as a root after performing certain iterations if it satisfies this condition. So, and then as soon as the condition is matched, we do not perform any iteration further. So we will stop. Maybe we will have this condition at the first iteration, maybe on a second or third. Wherever this condition match, we will stop our iterative work. And we said that, okay, this C is a desire. Now, what does this do? So what I'm saying, I can consider or I can take any value as a root of this equation if I put that function in a function and absolute value is less than or maybe equal to this quantity, that is 0.01. So if it is less than this or equal to this, we are happy. Less than condition is because we may get a 0, so that is much better. But this is our stopping criteria. In a book you can find that the difference between the two consecutive values are freezing. You can define the error like that as well, but I'm using this iteration. This is enough for our level of working. Okay, so you need stopping criteria when you have iterative process, because once the process start, it needs to be stopped somewhere, because it's just like a repeating itself. It is just like a wheel that is rotating about its axis, because it's trying to, on every rotation you get some better approximation, but question is when to stop that wheel. Greedy approach says that you have to get a exact answer, but it take ages. It take time. So we have to compromise on our accuracy. That's why we said we have to discuss what approximate. We can make it much better, but it take longer time. So we have to trade off. So we said, okay, this could be any value. You can say minus 12. Maybe you are solving using computers, so you said minus 12. You do not need to do manually, so you put the more strong condition. So this is how we have, but keep in mind this is not equal to 0. Okay, so this is how we have to define the stopping criteria, or we are using the stopping criteria for our method. So keep in mind this stopping criteria, because this stopping criteria will be used for other methods as well, because all other methods are also iterative in nature, but they are much better than the bisection method in case of the convergence. Now, what are the issues with the bisection method? It is very simple. No derivation, no calculation. You just need to find the two values which has this condition, and then you have to find the midpoint, and then you have to check again for each interval, whichever interval satisfy this condition. You have to find the midpoint of the interval, and then this process will be continue for rest of your life. So that's not rest of the life. I mean, for a longer time. So we, for to avoid this situation that we do not want to continue rest of the life, we have a stopping criteria. Okay, student. So this is how the bisection works. I will discuss examples of all the methods together so that we have a comparative study. My remarks about this method, which you can book in a book as well. This method is slow. Okay, it depends. So what does slow means here? First, we have to understand that thing as well, because we don't know the exact answer. Okay, so what making it slow? Because we are not moving in a systematic way ahead. We are moving in such a way that we have to improve our answer every time, because we are repeating, we are iteration, we are performing iteration. We have to repeat the same thing again and again such that we are getting a better answer. So this take time. Okay, so in case of number of iteration, if we have to compare that, we can say that the bisection method is slowest in case of number of iterations for a given interval. Okay, this is the important word which I will explain later. You have an interval and you have to compare all other methods that we learned in the later stage. Then you have to find the root in the same interval. So for a given interval, the bisection in method is slowest, and then all other methods we will discuss. Because what the slow means, it will reach to the root at any cost. But this is the one of the advantage as well. This is because of the bracketing, you always get a root. Not necessarily exact, but very close to the exact. But it is slow. It may take longer time. Okay, we will verify this in a later stage. So this is one remarks. In case of iterations, in case of iteration, this method is slow. However, this will never break down, because once the process start repeating, it is possible that you will have encounter a situation where you cannot find the root, although root exists, because of the failure of the method. There is no such thing. In bisection, you always get a root, but I don't know how many times it will take, how long it will take. So in case of iteration, it is slow. Okay, but other methods that we have to learn in the next class or in lecture number 6, we will notice that those methods are faster. They will reach to the root faster for a given condition, obviously, as compared to the bisection, but they have some issues with them. And we have to add a word that if they converge to the root, then they are faster. Okay, so they can break down as well, but in bisection there is no reason that it can break down, but it convergence is slow. Okay, so this is the concept. So the key point that I have selected this method to start with is to know you the sense of the problem. The problem is to find a root, very simple. So we have developed a very strong logic that we have to find 2 points such that f of a, f of b less than 0. That's, we call it bracket. We have bracketed the root, and then we have to find the midpoint. Then we have to find the further midpoint and midpoint and midpoint and midpoint. We will ultimately reach close to the root. This finding the same process again and again that can improve our answer is called iteration, and we have to perform the iterative job. So once we start the loop, that is iterative job, we need some stopping criteria. So we have defined the stopping criteria like that. after performing certain iteration, if we want to say that this is the root, then we have to ensure that this must satisfy our condition. Okay, so student, I'm ending the lecture here, and in the next lecture we will continue with some other methods, which is obviously the part. Not I'm ending the lecture here, which means next I have to start the on other method later on. Okay, so this method ends here. Thank you for your time.